StatQuest in an elevator, StatQuest out in the lawn, StatQuest in a wheelbarrow, StatQuest is everywhere. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to be talking about saturated models and deviance statistics. Note, there's a jackhammer blasting away at concrete right across the street from me. So if you hear a low rumbling noise, that's not my stomach, that's a jackhammer. If you're watching this video, chances are it is because you've already stumbled over something called the saturated model. You might have seen it in the context of the log likelihood-based R-squared formula, aka McFadden's pseudo R-squared. Or maybe you saw the saturated model in the formula for residual deviance. Or maybe you're just here for the song, StatQuest in an elevator. Regardless, in this video, I'll demystify the saturated model and a related concept, deviance statistics. Lastly, I'll explain why you can ignore the saturated model when you're doing logistic regression. Note, the saturated model and deviance statistics are part of generalized linear models and are intended to be used in a wide variety of situations, including, but not limited to, logistic regression, linear models, and other methods. So let's dive in. Imagine we weighed some mice. Now, just for the sake of this example, assume that we already know the standard deviation of the data. That means all we need to do to fit a normal curve to the data is estimate its mean. Bam! Here's our normal curve centered on the estimated mean value. The normal curve is a model of the data. We can use it, instead of the original data, to estimate probabilities and do statistical tests. Since we only had to estimate the mean for this model, we can say that the model has one parameter. And since a one-parameter model is as simple as it gets, we'll call it the null model. The likelihood of the data, given the null model, equals 0.03. And the log likelihood of the data given the null model equals the log of 0.03, which equals negative 3.51. We could also create a slightly fancier model by fitting two normal curves to the data. This model would have two parameters, one for each mean that we estimated. Psst! We're still assuming we do not have to estimate standard deviations. The likelihood of the data, given the fancier model, equals 3.57. And the log likelihood of the data given the fancier model equals the log of 3.57, which equals 1.27. We could also create a super fancy model for our data. The super fancy model has one parameter per data point. The super fancy model is called the saturated model because it maxes out the number of parameters we can estimate. The likelihood of the data, given the saturated model, equals 1,291.5. And the log likelihood of the data given the saturated model is the log of 1,291.5, which equals 7.16. So far, we've looked at the likelihood of the data using three different models. We looked at the likelihood of the data given the null model, which has only one parameter. We looked at the likelihood of the data given a model with two parameters. Let's call this the proposed model. Imagine it's the one we're really interested in using. And we looked at the likelihood of the data given the saturated model, which has one parameter per data point. By calculating the likelihood of the null model, we have a sense of the worst-case scenario. And by calculating the likelihood of the saturated model, we have a sense of the best case scenario. The likelihood of the saturated model is as high as it can be. Ideally, we want the likelihood of the data given our proposed model to be larger than the null model and close to the saturated model. When using likelihoods, we use the null and saturated models to determine whether the proposed model does a good job with the data. In other words, we use the null and saturated models to calculate R² and its p-value for the proposed model. Let's start by explaining the role that the saturated model plays in the log likelihood-based R². But before we get started, let me review one concept from the normal R², the one from linear regression calculated with the sums of squares of the residuals. With the normal R², the sums of squares for the null model determines the boundary for a bad fit. And when the model fits the data perfectly, the residuals are all 0, and the sums of squares for the proposed model equals 0. In other words, there is a fixed value, 0, that represents a boundary for the best a model can do. And when we plug in 0, we get R² equals 1. To summarize, the normal R² has a boundary for how poorly a model can perform, the sums of squares for the null model, and a fixed value, 0, that represents the best possible model. Now let's go back to talking about the log likelihood-based R². Just like before, the null model provides a boundary for how poor a model can perform. However, unlike the traditional R², there is no fixed value for an ideal fit that works in every situation. And that's where the saturated model comes in. The saturated model provides an upper bound for what an ideal fit is. Thus, if the proposed model is just as good as the saturated model, then the log likelihood of the proposed model will equal the log likelihood of the saturated model. And that makes the numerator the same as the denominator, and R² equals 1. Bam. But not a big bam, just a little bam for now. To see the problem that the saturated model solves in action, let's see what happens when we exclude it from the equation and plug in the log likelihood values that we've calculated so far. First, we plug in the log likelihood for the null model, that's negative 3.51. Then we plug in the log likelihood for the proposed model, that equals 1.27. Now just do the math. When we leave out the saturated model, the R² equals 1.36. Whoa! R² is only supposed to go from 0 to 1. We must be missing a scaling factor. Now let's redo the calculation, but this time let's plug in the value for the log likelihood of the saturated model. The other values are the same as before. And now we just do the math. This time, we got 0.45, a reasonable value that is between 0 and 1. This deserves a big bam. Bam! In summary, the log likelihood of the saturated model ensures that the R² value ranges between 0 and 1. Now let's talk about deviance, a concept related to the saturated model that will, ultimately, lead us to a p-value for the R². We're going to talk about two types of deviance, residual deviance and null deviance. Residual deviance is defined as 2 times the difference between the log likelihood of the saturated model and the log likelihood of the proposed model. The 2 times part makes the difference in these log likelihoods have a chi-squared distribution with degrees freedom equal to the difference in the number of parameters. In this case, the degrees of freedom is 4, the number of parameters in the saturated model, 6, minus the number of parameters in the proposed model, 2. To see the residual deviance in action, let's plug in the numbers. Boop, boop, beep, beep, boop, boop, beep, beep, boop, beep, 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 boop. Now we just do the math, and we get 11.78. Here's a chi-square distribution with 4 degrees of freedom. And here's where the residual deviance, 11.78, is on the x-axis. And the area under the curve from 11.78 to infinity is 0.02. So the p-value equals 0.02. And this means that the saturated model is significantly different from the proposed model. To be honest, I'm not a huge fan of this statistic in and of itself, but it is very common and, as we'll see in a bit, can be used as a stepping stone for calculating the p-value for r squared. Note, for this chi-square test to work correctly, the proposed model and the saturated model have to be nested. In other words, the proposed model has to be a simpler version of the saturated model, and not just any old model. Now let's talk about the null deviance. The null deviance is defined as 2 times the difference between the log likelihood of the saturated model and the log likelihood of the null model. Again, the 2 times part makes the difference in these log likelihoods have a chi-square distribution with degrees freedom equal to the difference in the number of parameters. In this case, the degrees of freedom is 5, the number of parameters in the saturated model, 6, minus the number of parameters in the null model, 1. To see the null deviance in action, let's plug in the numbers. Beep boop boop beep beep boop boop beep boop boop beep boop. Now we just do the math, and that gives us a value of 21.34. Here's a chi-square distribution with 5 degrees of freedom. And here's where the null deviance, 21.34, is on the x-axis. And the area under the curve from 21.34 to infinity is close to 0. So the p-value equals close to 0. Thus, the null and saturated models are significantly different. Just like for the residual deviance, I'm not a huge fan of this statistic in and of itself. However, it's very common and you can calculate the p-value for the log likelihood r squared from the difference in the deviances. This difference is a chi-square value with degrees freedom equal to the difference in the number of parameters for the proposed model and the null model. In this case, the degrees of freedom is 1, the number of parameters in the proposed model, 2, minus the number of parameters in the null model, 1. Plugging in the values for the null and residual deviances gives us 9.56. Here's a chi-square distribution with 1 degree of freedom. And here's where 9.56 is on the x-axis. And the area under the curve from 9.56 to infinity is 0.002. Thus, the p-value for the log likelihood r squared value we calculated before is 0.002. This means that not only does our model have a reasonable effect size, the r squared value, we know that that value is not by chance. Double bam! Note, there is more than one way to calculate the chi-squared value for the r squared. Alternatively, we can calculate the significance of the r squared directly by comparing the proposed model to the null model, since the null model is nested within the proposed model. The formula is simply 2 times the difference between the log likelihood of the proposed model and the log likelihood of the null model. Again, the 2 times part makes the difference in these log likelihoods have a chi-squared distribution with degrees freedom equal to the difference in the number of parameters. However, I mentioned the method that uses deviances because the null and residual deviances are very frequently reported. In contrast, the log likelihood of the proposed model and the log likelihood of the null model are not always reported. Little bam. Okay, we talked about the saturated model, residual deviance, and null deviance. Now let's talk about why you can ignore the saturated model entirely when you do logistic regression. When you do logistic regression, you're fitting a squiggle to your data and calculating the log likelihood of the data given that squiggle. However, with the saturated model, the squiggle fits the data perfectly. And the log likelihood of the data is 0, because the log of 1 equals 0. So the log likelihood is just a big sum of zeros. This means that the equation for the likelihood-based R-squared is this, which boils down to this simpler equation. Similarly, the equations for residual deviance and null deviance reduce to just 2 times the negative log likelihoods of the proposed model and the null model. Note, these deviances will ultimately be positive numbers because the likelihoods will be numbers between 0 and 1, and the log of a number between 0 and 1 is a negative number. And multiplying a negative number by -1 results in a positive number. Double bam! In summary, we talked about how the saturated model provides an upper bound on the log likelihood for a model. And that upper bound is useful for calculating a likelihood-based R-squared. However, with logistic regression, the upper bound is always going to be 0, so we can ignore it. We also talked about how residual and null deviance can be used to calculate the p-value for a likelihood-based R-squared. The difference between the null deviance and the residual deviance equals a chi-squared value with degrees of freedom equal to the number of parameters in the proposed model minus the number of parameters in the null model. Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more of them, please subscribe. And if you want to support StatQuest, please click the like button below and consider buying 1 or 2 of my original songs. Alright, until next time, quest on!